Some researchers interpret a new timeline of some of the formation's biggest eruptions as evidence that its activity is waning. The volcano below Yellowstone National Park is among the largest on the planet and has a history of generating huge eruptions. There have long been fears, many exaggerated, that it is only a matter of time before it blows, taking much of North America with it. But new research, published this month in the journal Geology, suggests that this volcanic menace may be losing its strength, and that you can be a bit less alarmed the next time you read a viral headline about that supervolcano out west. Yellowstone's volcano is the result of a hot spot, or a superheated area just below Earth's crust. These regions burn through tectonic plates that glide over them. This geological phenomenon is part of what gives Yellowstone its character, providing the steady flow of heat that warms groundwater and generates simmering, prismatic pools, cauldrons of boiling mud and geysers found throughout the national park. Unfortunately, ancient hotspot eruptions on continents are much more difficult to study than similar eruptions that took place out at sea, because they are more explosive. While researchers can see the path that Yellowstone burned as the hotspot migrated from Oregon across Idaho and into Wyoming, discerning one eruption from another has been a chore as most volcanic deposits are scattered across vast landscapes in a chaotic jumble. My predecessors thought these messy deposits might be related to one another, but nobody was sure, said Thomas Knott, the study's lead author and a geochemist at the University of Leicester in England. He set about the grueling task of fingerprinting volcanic samples from 50 sites in Idaho. Because each Yellowstone eruption would have involved different portions of the continent being melted, Dr. Knott reasoned that each eruption ought to be subtly different in its chemical profile. To gain further resolution beyond chemical analysis, his team looked at paleomagnetics. Because the iron from the hotspot was liquid when ejected, it oriented itself toward magnetic north upon eruption, and then got locked into place when it cooled. Because magnetic north has moved throughout Earth's history, Dr. Knott's team was able to determine when this iron was erupted. What they found transformed the timeline of some of the supervolcano's eruptions. Instead of a series of small eruptions that geologists have long thought took place as the hotspot migrated across Idaho, there had actually been two very big outbursts.